let's start with the paper that started the modern field of deep learning. So deep learning throughout the history came with various names. I think the last time was in 1985. People were working on neural networks a lot. But then the field died because at that time they didn't have the necessary computational power. Because these deep neural networks are not cheap to train. They are not cheap to evaluate. So the field died except for a handful of people who continued to work in that field. One of them was Jeffrey Hinton. The other one was LeCun doing convolutional neural networks. But then the field revived with this paper. And it changed its name totally to deep neural networks. And we're going to see why. What is the application that we are going to start with? And we're going to stick with it for a while. The application is image classification. So somebody gives us an image, let's say the image of a mite, and the algorithm should tell us, is it a mite or no? And there are like 1,000 classes. And these predictions, these are the predictions of the model. And we are keeping only the top 5. It's gonna say, with this probability, that's a mite. With this probability, that's a black widow, cockroach, tick, or starfish. With these probabilities, and the red is actually the underlying truth. So these are test data. And the type of classes that you're gonna see are mite, container ship, motor scooter, leopard, and so on. And you want to write an algorithm that does that. I bet some of you have tried to use Google Scholar at some point, and then you saw a window popping up saying that, prove to me that you're a human. And the question that they're gonna ask is, click on all the traffic lights in the images that you see. So what does it mean? To test whether you're a human, they give you a classification algorithm. Computers are really good at solving algorithmic stuff. Like they're really good at solving PDEs, ODEs, molecular dynamics. But they're not capable, they were not capable of solving easy stuff. Easy for human. For a human, it's really easy to tell apart a leopard and a motor scooter. But for a computer, it's not. So we're gonna start with this classification task. And I'm gonna have a quote from that paper. It's actually from Jeffrey Hinton. It says, to learn about thousands of objects from millions of images, that data set that you're seeing is ImageNet data set. It has millions of images. And there are thousands of objects. There are actually 1,000 objects. These are the labels. It continues with saying, we need a model with a large learning capacity. That makes sense because you have millions of images. You need a model to be able to memorize it, memorize your data. However, the immense complexity of the object recognition task means that this problem cannot be specified, even by a data set as large as ImageNet. So our model should have a lot of prior knowledge to compensate for all the data that we don't have. The key word here is the prior knowledge that I want to emphasize. Deep learning works, but it doesn't work by random. It's not like you throw at it millions of data and it's going to work for us. So you have to be very smart about the prior that you choose. Convolutional neural networks, they make strong and mostly correct assumptions about the nature of images. What are the properties of an image? For instance, the statistics are stationary. So maybe you have a filter here, and the same filter you can apply to all the neighborhoods that you might see in your data. And they are local. This pixel is gonna depend more on this point compared to a point that is really far away. So CNNs are making mostly correct assumptions. And that's why people use CNNs. But what is a CNN? And first of all, what is an image? An image is a tensor. And tensor is a generalization of matrices. So a tensor is going to be 224 by 224. That's the width of your image. That's the height of the image. But then it has 3 channels, red, green, blue. And when you combine those channels, that's going to give you the color that you see here. So that's the input to the algorithm. The output is a probability. It's actually a probability distribution over 1,000 objects, and the objects are mite, container ship, motor scooter, and you name it. And there are 1,000 of them. You want to put a probability distribution on that. That's why the summation of your probabilities has to be 1, and the probabilities are always bigger than 0, bigger than or equal. So an image goes in, a probability comes out. That with this probability, that's a mite. With this probability, that's a black widow, and so on. That's the input to the algorithm. That's the output, 1,000 numbers that add up to 1. What happens in the middle is a bunch of convolutions and max poolings. So what is a convolution? You have a kernel that's 11 by 11, let's say. So you put a kernel of 11 by 11 here. So the dimension of your kernel is going to be 11 by 11 by 3. And you just multiply this kernel by that window of your image, pointwise. Then you summation it. You do a summation on that, and that's going to give you a number. So that's just the inner product of this filter and that part of the image. And then you keep doing that. You keep sliding this window on your image. And that's going to fill out 1 slice out of these 48 slices. Then you're going to have 48, basically 47 other filters. So what does this mean? Your filter is going to be 11 by 11 by 3 by 48. That's your filter, and that's going to help you fill out this box here. That's going to give you another tensor. And forget about the top convolutions. We're going to go back to that later. Now you want to keep shrinking your images. You don't want to keep working with 224 by 224 images all the time. You try to keep shrinking, and the way that you do it is by max pooling, for instance, or average pooling, or you name it. The paper is using max pooling. Then you're gonna have another convolution and so on up until the end. You end up with a dense layer, which is basically you're flattening whatever that you're left with. You're flattening this cube into a vector. And then the rest of it is just linear combinations and nonlinear activations. So at that time, they had to divide their neural network into two components, because at that time, the GPUs were not powerful enough yet. This was the first paper in deep learning. So they used two GPUs. One of them is responsible for this part of the neural network. The other one is responsible for the other part. So they divide it into two parts. These are independent. And at some points, these two GPUs are going to communicate. This is one part that they're communicating, and this is the other part. But the rest of it is just parallel. So it's going to help them increase the capacity of their neural network. Why is that important? Because they wanted to have a large capacity for their neural network. I think it's easier if you start with one-by-one convolutions to help you understand what is actually a convolution. The input to a one-by-one convolution is X. The output is Y. X is going to be H by W by C. That is the height, that's the width, that's the number of channels. For instance, here it's 224 by 224 by 3. 224, 224 by 3. The output is going to be 224, 224 by, I don't know, 48. One simple way of dealing with that is just pointwise, basically pixel-wise. You take a pixel, and that pixel is going to be in R3, so it's three-dimensional. So it's a pixel, but everything here has a dimension. The dimension of that pixel is 3. Now you can have a bunch of weights that's going to take you from dimension 3 to dimension 48. And this is just vector multiplication. And the output is going to be another pixel that has dimension 48. So this is one-by-one convolution. And this is actually the dense stuff that you see here. These are all, you can think of them as one-by-one convolutions. One-by-one convolution is sometimes also called pixel-wise convolution. How do you generalize this into, let's say, 3 by 3? If I tell you how to generalize it to 3 by 3, then you know how to generalize it to any kernel size that you like, k by k. And sorry for the abuse of notation here. This W stands for weights. That W is for width of the image. But that's okay. That's not a bad mistake to make. So now we want to know what is the output of our 3 by 3 convolution at a pixel point. You take a window, let's say it's a window of 3 by 3. Here it's 11 by 11. It means that each one of these is a pixel. And what is going to be the dimension? The dimension is going to be on RC. Each one of these vectors is in RC for instance, is 3-dimensional or 48-dimensional or 128-dimensional. You can do the same thing. You can multiply it by a vector, by a matrix, to change the dimension from C to F. For instance, from 48 to 128, you can just multiply it by a matrix. But then you have to do it 9 times because you have 9 pixels around a single pixel. The one on the left, the one on the right, the one immediately on top of it, the one below it, the one to the left top corner, right left corner, and so on. You get the idea. There are 9 of them. All of them are vectors, and you have this many matrices, 9 matrices. For 1-by-1 convolution, you had only 1 matrix. Here you have 9 matrices. And that's going to give you a 3-by-3 convolution. And that's the main operation that's helping you jump from one layer to the other layer. What is the loss function here? What are the parameters first? The parameters are these weights and biases. The biases I'm removing. I'm not including them here. And those are going to constitute your thetas. And the loss function, what do we want to do? We want to maximize the likelihood of each image. Our training data is in this form. There is an image of a mite and the corresponding label, little in and capital In. Capital In is an image. N is nth data point. In is its label, which is a value from 1 to 1000. And then you want to maximize that probability, or you want to maximize the log of that probability. In machine learning, we would like to minimize. That's why you multiply by a negative sign. The cool thing is that if you increase one of these PIs, the rest of them have to go down because the summation has to be a 1. That's your loss function. How do you train it? Using the methods that we just went through. And in the end, their method beat all the other previous methods that were not using neural networks, and by a large margin. These are huge margins. So before deep learning, people were doing featureization by hand. Basically, a bag of visual words would be their features, and most of their time would be spent on featureizing images. But now deep learning does the featuring on its own, featureizing on its own, and it's beating the hell out of the previous methods.
Can you explain that table just a little more? Like what do those numbers represent, and what is top 1 and top 5?
That's a good question. The model is going to predict 5 outputs, as you can see here, the 5 most probable ones. For instance, for this image, it's predicting mite, black widow, cockroach, tick, and starfish. If the actual image is appearing here, that's going to give you a positive case. It means that your algorithm did it right. If mite doesn't happen here in the predictions, that's a negative point for the algorithm. So the algorithm is failing. So mite is now appearing in the predictions of the model in the top 5 ones. So it's a success. Even here, that's a success. And this is a failure. Cherry is not appearing in the, so the algorithm, you're gonna show it a bunch of test points, test images. You know the ground truth, and then you can count the number of times that the algorithm was successful versus the number of times that it wasn't successful. And this is just the top 5 accuracy, the number of times that the algorithm was successful divided by the number of times that you actually tested your algorithm. the number of test data.
Seems like that table's a failure rate. If you said the CNN method is doing better,
Yes.
wouldn't we want a higher number?
Yes, so sorry, this is the error rate. You're right. So this is the number of times that the algorithm is making an error. Out of 100 cases, the algorithm is making 17 errors. So
Thanks.
17 times, cherry was not one of the predictions of the algorithm. And top 1 is a tougher metric compared to top 5. You just look at the top 1 prediction. For instance, this is a failure case. The algorithm is predicting the underlying truth is mushroom. The algorithm is telling us that's an agaric, and that's a failed case. That's why this number is bigger than the other. So these are the failed cases, top 1 error and top 5 error. I think we are 1 minute over time. For those of you who want to leave, you're more than welcome to leave. And for those of you who have questions, I will be around for a while.
I have a number of questions. So in this architecture picture, it looks like there's 48, what did you call them? Convolutional fields to go from the original images to that first layer where it's 55 by 55 by 48. So there's 48 different filters there.
Exactly.
And
So
then the next time around, when you do the max pooling, are you maximizing all of the 5 dimensions in like the original width height and then leaving those 48 dimensions alone? So are you collapsing a 5 by 5 down to 1 pixel, or are you collapsing a 5 by 5 by 48 block down to 1 pixel?
So you are gonna keep actually this 5 by 5, and then it's gonna do it per filter. So this one, at the end of the max pooling, you're gonna have still 48 dimensions.
Okay.
But then what the max pooling does is gonna turn that into 27 by 27, because every 5 by 5 window is gonna collapse into 1.
Wouldn't that reduce the dimension by a lot more?
That's gonna reduce the height and width of the dimensions.
If you're taking wouldn't it be 11 by 11? Because you could have 11 such windows that were 5 by 5.
No, so that depends on the stride. So
Okay. So you're allowing for overlap.
exactly.
Okay.
So you might be striding 1 by 1.
And then would it reduce the dimension at all? Or I guess when you get towards the boundaries, you run out of room, and so no matter what, it's going to reduce the dimension
when you
by
run
a small amount?
boundaries, that's called padding.
Okay.
That's a good point. So these are all the delicate points when it comes to convolutions. When you're at the boundary, you might either decide to pad or not pad, or pad differently with a bunch of zeros or no. That's how we deal with boundary conditions. If you want to reduce the dimension, reduce the pixels, then you have to stride by more than 1. So it has to be a stride of 2 or a 3.
Okay, so then we've done convolution once and pooling once to get to where your cursor is right now, where it's 55 by 55 by 48. And then getting to the next one over, it applied another, how many filters there? I just have a hard time imagining this this depth dimension. We went from 3 to 48 and then up to 128 for the depth of this. Yeah. So what would be the next operation?
So there is one max pooling. The dimension is going to be still 48. But then from 48 to 128, there is another convolution.
Okay.
And that's going to be 5 by 5 convolution.
Got it. Would it be, how many filters there? 128 filters?
Exactly. So there are going to be 128 filters. So
Okay.
C is denoting 48, F is denoting 128. And then
Okay.
they keep changing from one layer to the other one.
And then at S down in this formula with the double sum, S is that stride length value.
That's the stride exactly. That's why you're gonna reduce the number of pixels if your stride is bigger than 1. If
Got
it's
it.
2, then the number of pixels is gonna shrink.
Yeah. Understood. And then like the padding or non-padding is why there's a little bit of weirdness with like 55 going to 27 to 13 and so on. Okay, that helps a lot.
Exactly. So the way that you deal with boundary conditions is important.
This seems extremely hard to do with general pictures on the internet where you don't know the dimensions coming in, because it seems like this architecture, someone had to think about it a whole lot about the exact strides and when to stride by 1 or 2 or 3 or 4 and padding and whatnot. And if you gave me an arbitrary,
yeah, if you look at it, it's a 2012 paper, and people have made a lot of progress. Actually, the convolution operation doesn't depend on the pixels.
okay,
So they're actually to get it independent from the image size.
but you couldn't necessarily take this exact network and pass in anything except for a 224 by 224.
That's correct.
Image.
So you need to change your neural network structure. That's correct.
Which sounds expensive. Are there ways then, like what's the best way then of classifying a general image on the internet where it's going to be 1 or 10 megapixels?
That one, we have the whole semester in front of us. So we're going to have different types of neural networks. This one is going to be called AlexNet. Why? Because the first author is Alex. So it's an AlexNet. We're going to see different versions of neural networks as we go along.
Fair enough. I could imagine that you could just do some kind of averaging right off the bat to get the dimensions down to what you need it to be.
Probably.
You could even go the other way. You can upscale a small image and make it a bigger image.
Yeah.
Yes, so that's called deconvolution. We're going to see that. And each one has its own applications. For this case, you have an image, and the output is a bunch of numbers, 1,000 numbers. So whatever that you do, the input should be an image. Whatever that you do in between probably matters, but the end, it has to be 1,000 numbers that add up to 1.
I've seen this before though, where you can have the output be just a single scalar, and then you are trying to get that scalar closest to a 0 or a 1 or a 2 or up through like 999. Does that work any differently than this?
That approach is useful when you want to do, maybe there are 2 things in your image. Maybe there is a mite next to a container ship. Then the probability shouldn't add to 1. That approach is useful when you have multiple stuff in your images.
Got it. Got it.
But here, there is only one ground truth. It's a mite. It's a container ship. There is one dominant.
Well,
object.
That cherry example seems a little mean.
I was
the cherry with the.
Yes. So the data is very important. Okay. The deep learning is going to depend on your data.
Yeah, that was going to be my question, is how do you may not have enough time to sink into qualifying your data set. So how do you find images like the cherry example, or make sure there aren't any other pathological imagery in your data set, like the motor scooter stands out to me because that seems like a case where it's not clear that the motor scooter is the subject of the photo. So it might,
yes, you're right.
Might associate the person riding on the motorcycle as the motorcycle instead of the actual scooter. How do
Yeah.
you look for examples and make sure you can account for them while you're training this network?
So the thing is, that's why in the overview, I was saying that the source code is your data. So usually if there are any bugs in your code, in the output of your algorithm, the actual thing that you want to deploy is your data. So you have to go debug your data. Perhaps
Nice.
remove that case. Perhaps add more cases that you like, okay?
I see. I
So
see.
the source code is your data.
So the answer is sanitize the data set.
Exactly. So data matters a lot.
Got it.
Can I ask real quick, in this image you have here showing the CNN, none of the, if I'm correct, none of the max pooling steps are shown. It's just like they're implicit, but it's each sort of dotted arrow step is a convolution. Is that correct?
Yes, that's correct. So
Okay.
everything that you see is a convolution. The max pooling stuff are not shown.
Okay.
So if you want to see the exact formula and the exact structure of AlexNet, so there is a table in the paper that's actually specifying what is the input dimension, what is the output dimension, what is max pooling doing, and so on.
Okay, thanks.
Yes, you're right. The max pooling stuff is not shown here.
Is there any intuition behind why they set up the model architecture this way?
Yes, one of the intuitions is that they wanted to put a large model on 2 GPUs. That's why you have 2 parallel structures. The other intuition is that, see these parameters and the sliding window that you have, they are local, they are stationary. So it's the same weights and biases that you're gonna keep sliding. So the convolution stuff is really parameter efficient.
But
Because
in terms of like the amount of convolutional like layers and like the amount of pooling layers, is that something they discovered through like trial and error, or was it more of like from the size of the image they can have that many layers?
there is a size of the image, and there is how many layers, how many parameters they can fit on their GPUs. So usually with these types of neural networks, the deeper is the better when it comes to classification. Okay, if they could have deeper structure, they would actually do it, but it was 2012.
Gotcha, makes sense. Thanks.
In general, I don't know if this is something we'll talk about during the semester, but like in general, choosing the structure of your network model seems quite arbitrary to me. How and why people choose certain model structures over others, like why insert, you know, layer type X and layer type Y right after each other? Is that just something you learn sort of the more you do it?
I'm gonna be talking about neural network structure, like these type of choices that you make, for a while in this course.
Mm-hmm.
For at least a month, we are gonna be talking about the structure.
Okay, and why you would choose when you're building your own model, why you would choose to do certain
what
things.
are the building blocks, how to study them. So I'm gonna spend a lot of time on that so that it's not like black magic. There are actually some intuition behind it, like stationarity of statistics, locality of pixel dependence, and so on. The other is locally translation invariant. If you shift this image a little bit higher, it's still a container ship, okay? If you take this leopard and shift it to the left, it's still a leopard. Okay, the label doesn't change. And that's where max pooling is helping us, because it says that I don't care what is in this window. As long as it's local, I'm going to collapse everything into one number.
Okay.
Are there ways to translate the structure of your neural network into something that you can take the gradient of itself?
You mean the gradients by hand?
Well, I mean, like, you know, suppose you learn the size of the convolutional filters or the depth of each layer.
Oh, you want to learn it from data. That's going to be automatic machine learning. We're going to go through that
Great.
later. If you take a look at the topics, that's there. We are going to cover it. So any other questions?
Thanks, everybody.
Yeah, thank you.
Yeah, thank you.